this thing, and it's now we're at PDEs. If you can do PDEs, everything else you can handle. So this is the end of the food chain. All right, now there are various forms of PDEs. All right, what I will use will be the general transport equation, which contains a first derivative and a second derivative, like a diffusion term. It's important that you be able to recognize the PDE, and because you need to know what particular numerical technique to use for that type of equation. You have to also be able to recognize the degree and the order of an equation. All right, so here's an equation. All right, following equation is simple PDE. What's its degree and order? All right, anybody want to take a stab?
Second degree.
Two degrees in second order.
How many say second order? All right, why is it second order?
There's a second derivative.
All right, what degree? Remember what degree is?
It's two, right? Because there's two types of derivatives.
No?
Two. No.
Try again.
Three, because there's two types of variables.
No.
First degree.
I'm questioning your math skills. You go to the highest derivative and you look at the order of the power. What's the power on the highest derivative?
2.
1.
One. Yes.
Right? So this is a second order first degree.
Because it's the highest.
Get the idea?
Second derivative.
See, that is the second derivative of u with respect to x to the first power.
Yeah.
All right?
It was x squared.
Okay. Order of an equation determined by the highest derivative. Second order equation would have a second derivative, just like you saw. Degree is determined by the highest power of the highest derivative. Remember that. All right? Highest power of the highest derivative. What's the degree and order of the following equations? What's the degree and order of that equation?
First degree, second order.
First degree, second order. Correct. How about this one?
First degree, second order.
Why?
Because the highest derivative is powerful.
Right? Yeah. So just think, if I put this on the next exam, all those that aren't here today will probably miss that. You guys will have it. All right, these things should be familiar to you. If you haven't seen them, well, welcome. You've seen them now. You will see them again, I'm sure. That's the 1D wave equation. If you've had acoustics, you've probably seen that already from Doug Reynolds. Okay. That's the 1D heat equation. All right, it looks familiar, or looks the same, right? That's the diffusion coefficient, or what we refer to as the conductivity, right? That's a first derivative, that's a second derivative. That's Laplace's equation. All right, now if I take that equation and I move it down here and I put everything on the left-hand side, you notice that that would have a minus sign, right? That's how you can tell the difference between Laplace's equation and the wave equation. It's in that sign. All right? That's Poisson's equation. What's the difference? You have something it's equal to some function on the right-hand side or some value. It's not equal to 0. That's the difference between Laplace and Poisson's equation. All right, wave equation is hyperbolic. Heat equation is parabolic. Laplace and Poisson equations are elliptic. Those are the three types of equations. Circle those big time. You have one of three choices: elliptic, parabolic, or hyperbolic. Depending upon the type of equation will then dictate the type of technique or numerical method that you should be using. How many of you remember this thing? Saw that in calculus. So it's basically determining from the coefficients if the equation is elliptic, parabolic, or hyperbolic. All right, so if you have terms that have second derivatives in there, you're fine. By the way, do you ever see D, E, or F showing up in these things? Okay, you're gonna see a little dilemma that you run into in a moment. As long as you've got second derivatives in there, you're all right because you can follow this rule. It's when you don't have them that it can get a little tricky. Okay, so what do you do when you have two equations like this? What kinds of equations are those? You've got one of three choices. What do you guys say? Well, we're doing a stochastic process here, I guess. So you're saying it's what? Elliptic? Parabolic?
Parabolic.
It's parabolic.
How many say parabolic?
Wait.
There's no abstention. How many think
No,
that they're
no,
elliptic?
it's not parabolic.
I'll say it.
So that means the rest of you who didn't vote have to assume that it's hyperbolic?
You go.
Is that right? Okay, you want to put your car keys out there? How confident are you? Okay.
Because of you, right?
Those are first derivative terms. Obviously, no second derivatives. They're hyperbolic. Right? Hyperbolic.
How can that be if the A, B, and C coefficients are all zero?
I told you, you have a dilemma when you run into equations like this, right? And so there's a way to figure it out if you have to. Just remember, when you see equations of first derivatives like this, they're hyperbolic. But if you're not sure, you can try it this way. All right, so if I have two equations with variables u and v, all right, I can solve this as an eigenvalue problem. How many of you had eigenvalues before?
Once.
Sometime or other, somewhere in there. You should have had matrices, by the way, in solving for eigenvalues. All right, so I've got the derivative of w with respect to x, derivative of w with respect to y. Here are the coefficients that come from those two equations that you saw, a's and b's. I can rewrite this so that it looks like this. Now, what does this mean? What's the -1 mean? Inverse. If I call that m and I call that k, then I've got the inverse times m. I've rearranged this equation so it looks like this. Now, you can handle 2 by 2s, I know, because we went through that. And so you can actually find the inverse of that. I can rewrite this so it looks like this, where n is m divided by that, or times that inverse. That's how you do that. That's how you determine that. What can happen is that you can get equations that look like this. Find out from the following equation, is it parabolic, hyperbolic, or elliptic? What do you think?
What does that M stand for?
That happens to be Mach number. That doesn't matter to you, it's just a coefficient right now.
Hyperbolic still?
I'd vote on hyperbolic. See any second derivatives?
No.
All right. Now what happens here is this coefficient. What goes on?
You remember what you said?
If the Mach number is less than 1, then that's positive value. If the Mach number is greater than 1, what happens?
Negative.
Yeah. You people recognize this equation right here, those terms? It's a continuity equation for an incompressible flow. So what happens when you have a compressible flow is you can wind up with this coefficient that's setting out here. And you can see that if your totally subsonic flow, very slow flow, right, that turns negligible. So you just have the continuity equation for an incompressible flow. Oh, gee, what happened there? Hold on. The following equations mathematically describe the motion of incompressible laminar fluid and energy. Equation for fluid motion. Okay, this is called the Navier-Stokes equation, except you don't have these goofy things in here. that should be a dot. So del dot V is equal to du dx, dv, dy, dw, dz. That's the continuity equation. That's normally referred to as a dilatation term, but in incompressible flow, we think of it as del dot V equals 0. So you've got first derivatives that show up of the components of u, v, and w, right? 3 components. This is the momentum equation for the velocity, actually for u here. So what you've got is the left-hand side consists of these first derivative terms. The right-hand side consists of these second derivative terms. I don't know what those are. I think they're supposed to be brackets. And so there's the viscosity. So you've got an equation that contains second derivative and first derivative terms. Same thing with energy or temperature down here. So you've got these first derivative terms, second derivative terms. So there's the conduction or the exchange coefficient here. What kind of equations are these? Right? What's the degree and order of these equations?
2 and 2.
Second order, first degree, correct. Right? Because you've got second derivative terms showing up here. They're to the first power. Now, what type of equation? Is it parabolic? Is it hyperbolic? Or is it elliptic?
Elliptic.
It's parabolic.
Why isn't elliptic? I mean, you got something squared and you got something equals on the left.
Time. That's.
All right, so how many say parabolic? How many say elliptic? So that means the rest of you assume that it's hyperbolic? There's no abstention. It's a mix.
No, trick question.
Trick question. That's because it's fluid flow. That's because fluid flow is difficult. You've got nonlinear equations setting up here. And so if you don't have any viscous terms, you have these first derivative terms and the pressure gradient.
So it's hyperbolic.
That part of the equation, that's known as Euler's equation. That's hyperbolic. You can actually solve Euler's equation to calculate shock locations. What happens when you start throwing on the viscous terms is that you're now accounting for the viscous effects or the boundary layer that could grow along the surface of an object. Now, as this thing progresses in time, this creates an elliptic solution in space that you're marching as you kind of go up in time. So you have a parabolic elliptic equation. And this equation, what makes it so nasty, is that depending on the flow rate, it can flip, or it can go transition from hyperbolic to elliptic or parabolic. All right? That's why solving these kinds of equations are very, very difficult. So you have to have a technique that we call robust. Robust means that it's going to handle those wide ranges of conditions that these equations can experience or that you set up for your problem. Now you can write the equation for species transport in a similar fashion. Here this happens to be concentration. It's a scalar quantity. Scalar equations are equations like temperature or concentration. Right? Vector equations like the velocity, because how many components in velocity? U, v, and w in 3D, so it's vector. These things on the left-hand side are called advection terms. In mathematics, it's called advection. In engineering, depending on the type of engineering that you're in, they may be called convection. You have to be careful because sometimes convection implies heat. And so if you're talking about convection, you may think, oh, there's heat involved. And maybe the person was referring to just these terms. That's why when you say advection, you know exactly what they're talking about. It means those first derivative terms. So if you notice, here are the advection terms, here are the diffusion terms. These are second order, right? Because they're second derivative terms sitting here. That's a source or sink term. These equations all look the same. If you noticed, in the flow equations or in the temperature equation, you had these things sitting over here on the left-hand side, these second derivative terms sitting on the right-hand side. So what you want is a numerical method that can solve the general class of equations. So you can handle fluids, heat transfer, structures, whatever. Because most of the equations will fall into that general type category or form. Now, other equations that you might have to deal with, particularly if you're talking about fluids, is P equal rho RT. That's called what? Equation of state. All right, so I can relate back the pressure as a function of temperature. What happens when if you notice in the momentum equations, the fluid equations, or the velocities, you have in 2D, let's just look at 2D. I have a U component and I have a V component. What else was there that showed up in that equation? Pressure gradient. Yeah, pressure. So what you have is an equation for the U component, an equation for the V component. But what do you do about pressure? If you're in compressible flow, you can get pressure from here. But if you're in incompressible flow, you can't do that. Because it's probably not a gas if you're dealing with water. So you have to come up with another means to solve for pressure. That's what makes them so difficult. So if you look at these time-dependent PDEs, they have the same parts. A transient term, as I mentioned, the advection terms, the diffusion terms, and then you have a source sink. Right? In the heat transfer equation or energy equation, it's probably labeled as Q. That's the general form of the equations. Now that G should be a dot. Sorry about that. So d phi dt plus v dot del phi is equal to k del squared phi plus s. Phi is the unknown variable, right? It can be anything. It can be temperature, concentration, velocities. That's the general form of the equation. V is the velocity vector, so here you have U, V, W, and 3D. K is the diffusion coefficient. All right, S is the source sink term. All right, sometimes that's called the conductivity and heat transfer. That general equation can either be a scalar or a vector equation, depending on what phi is. So if I take phi and I say, well, phi is going to be temperature, then I have a scalar equation. But if phi is a velocity, then I have uv. And remember, when I have something u times du dx, or v times du dx, or whatever, that's nonlinear. When I have something like u times dt dx, or v times dt dy, that's scalar. It makes a big difference. So you're solving either linear equations or nonlinear equations. We're going to discretize the equation using finite difference, finite volume, and finite element. Those are the three standard methods. The ones that you will use primarily in structural analysis or solid mechanics will likely be the finite element method. And that's because you've got kind of screwy surfaces, irregular shapes. When you discretize those shapes, the finite element method is the best way to go about doing it. When you have very simple geometries, rectangles, boxes, things in which it's easy to make lines orthogonal. What do I mean by that? Lines that are going to cross perpendicular. Then you want to go to the very simple methods. And you can do that by finite differences or finite volumes. Remember what Laxmi talked about when he said computational geometry. You now have to have a mesh. And so you're creating a mesh of the problem domain, or the problem that you want to try to solve. So you're taking those partial differential equations and you're going to solve for the intersections, the node points where those lines will cross, the mesh lines. Those are the unknowns. And so if you have a lot of unknowns, guess what? You might have a big matrix to solve. If you got a very small geometry, well, it could be relatively small, quick, you can do it on the PC. Finite difference method. That's the simplest and the first that we will look at. It's quite popular, it's very easy to formulate. Guess how you formulate it? Taylor series. That's why you learn Taylor series. First and second order approximations. You remember how to do that? From the Taylor series, what would be the first derivative approximation? You can do it as a forward series, a backward series. What happens when you subtract one from the other? What do you get? Central difference. That's the most popular technique in doing the solutions of PDEs, is a central difference. The mesh, it's very easy to construct. You can do it in 4 lines of code. You use 2 nested do loops. What do I mean by a do loop? All right? So if I have 1 to n in the x direction and 1 to m in the y direction, do I equal 1 to n, do j equal 1 to m. X equal x I minus 1 plus delta x, y equal y plus delta y. In, I'm done. I've created the mesh.
You can't just say and, you have to say and.
Has to be.
Pins. Details. You guys are killing me on the details. All right, the finite volume method. 1 node for each element. It's located within the volume or at the centroid of this element that you created, or volume, from the intersections of the rows and columns, the lines. All right, so when I talk about point discretization in a finite difference method, I mean the intersections of the lines of the mesh. When I talk about a controlled volume, or a finite volume, I'm talking about the centroid within that array that has been created. You can compute the change of property for each of these volumes or centroids. You can compute inflow, outflow. It's because in a finite volume, you're talking about the flux that goes into the volume, the flux that comes out. So this technique is a conservation technique. It's a method that conserves mass. That means you don't have extraneous stuff that's showing up or appearing, probably due to error and so forth, that you would have in your calculation from the truncated Taylor series that you made. You can add volume sources or sinks for each element, accumulation, outflow. This is what I mean by the mass balance. It is very good, and it is the most popular technique now being used in commercial codes for fluids. It has some basis in physics, of course, where you're dealing with fluxes and sources and areas and all sorts of things like that. Let's go that way. All right, finite element method. You use multiple nodes for each element. These are placed at the boundaries of the element. Now, those type of elements are called serendipity. When you hear that name serendipity, it means, oh, I've got these things located on the exterior of an element. When I talk about Lagrangian, it means I have a node point that's setting inside these elements. Right, I'll show you, I'll draw one in a minute. You use what are known as trial and basis functions. These are polynomials. This is why you did polynomial interpolation. And it allows you to go up in order from linear, quadratic, cubic. Guess what? You can do the same thing with these elements. You can have linears, quadratic, cubics, as high as you want to go. That's one of the strengths of this method, is that it allows you to bump up the order of the element, where in a finite difference, central difference, what's the order of accuracy? Second order. That's it. We compute the coefficients of the functional to satisfy the governing equation at the nodes. There is a lot more rooted in the mathematics of this. It's an integral method. And so from that method, you can spin off a lot of techniques, including, in fact, the finite difference method if you want. But there's a lot more to it as far as a richness of mathematics. There's no guarantee of local mass balance, but it has global conservation. Right? The Glerkin weighted residual method, MWR, this is the technique that you will most likely run across. And it's called a residual method. It just means that if I integrate the equation that I'm solving over whatever the space would be, 1D, 2D, or 3D, and I set it equal to 0, it means I'm setting the residual errors, I'm setting equal to 0. Now, when you think of it, you go, residual errors, where did those come from? Remember Taylor series? You have to go out to infinity, right, to capture the exact mathematics, so there's always a residual left over. You're doing the same thing here. When you're saying in finite elements, I'm going to set the residual equal to 0, and I'm going to spread that error throughout the whole problem domain. I'm not going to localize it like I do in a finite difference approach, right? This works perfectly for unstructured meshes. That's what makes it so popular. You model the actual physical geometry. You don't have to transform it into something that's going to be a box or a rectangle or whatever. All three the methods divide the physical domain into a number of volumes or elements. That's what we mean by a mesh. And that's what Laxmi Gowali was talking to you about, is trying to come up with a means to create the optimal mesh for the problem geometry that you're trying to solve. In 3D, you generally use hexahedrals or tetrahedrals. How many of you remember what a hexahedral is?
6.
It's a brick, right? A hexahedral just means brick, right? Or a rectangle, or a box, or whatever. How about a tetrahedral?
3.
How many points in a tetrahedral? 4. How many points in a pyramid?
4. 5.
5.
Oh.
Right?
Yeah.
Quadrilaterals or triangles in 2D, and you've seen those. You've actually probably seen pictures of meshes of triangles and quadrilaterals. You can use other shapes, particularly in finite elements, that you're not constrained to just triangles or quads or tetrahedrons or hexahedrals. You can have other shapes, but you have to write particular functions to describe them. The finite volume and the finite element are converging, and what's happening is that the finite volume method has now picked up, and it works on unstructured meshes. That means they're not uniform or irregular shapes, kind of like finite elements, because they're using the finite element mesh generators that have been around for a long, long time. So they've integrated that into the finite volume method. Most commercial codes, as I said, are based on finite volume in the fluids area. Right? There are some pretty nice finite element codes around that will do fluids as well. Now, which one? Finite difference. Physical geometry is simple. It's a rectangle. You can create the mesh by observation. You can set up your rows and columns very quickly. You need a quick solution. You use the finite volume method when you want to ensure that you're conserving mass and energy. That is, you don't have things that are suddenly cropping up or appearing from somewhere in the numerical roundoff or the truncation that you've encountered in, say, the finite difference approach. It's useful in high-speed flows with shocks, phase interfaces, and so forth. And also very handy when you're doing chemical combustion or reaction-type problems. Finite element method, when the flow is inherently smooth and you want a higher accuracy. You can have mixed element shapes. It means you can have a triangle that's next to a quadrilateral. You can have higher order elements with lower order elements. The nice thing is it's really flexible. You can do a lot with it, where you're not constrained to a particular type of discretization that you are in these other two methods. The physical geometry can be complex, so you go in and set up the mesh generator, and what you see is what you're going to model. Now, finite difference method. Let's begin with that one. It's an old numerical approximation. It's been used with structured meshes. Now, what do I mean by structured meshes?
What's on a grid?
Okay, so if I have a rectangle, and let me see if I have this. I have a physical domain that is orthogonal in the sense that when I put in my columns, this would be my mesh, and I put in my rows, everything crosses at 90 degrees. All right, so that's what I mean by a structured mesh. Now, they don't have to be the same delta x or delta y. That would be a delta x. That would be a delta y. Right? When they're the same, then it's uniform. They don't have to be uniform. The only constraint that you have here is that these things have to be orthogonal. So what I'm solving for are the node points that are created by the mesh. That is called a mesh. Now there's a computational molecule that you can set up for doing central differences, and once you see it, you kind of remember it. It's really just based on what you did from Taylor series. In doing a finite difference simulation, or even setting up the equations, it's very easy to do so. When you establish the equations from a finite difference or a Taylor series approximation, that's called discretization. What you're creating is an algorithm. And that algorithm kind of looks like pseudocode if you look at your book. And so you go, oh, here's the rule for actually solving for these unknowns as a function of where they're located within that mesh. You also can use very simple matrix solvers for this. One of them is the Thomas algorithm. Remember what the Thomas algorithm does? Tri-diagonals. Now, why did you do tri-diagonals? You did those when you were solving for splines, because there are 3 unknowns in a spline. And so what you did was create a matrix that would be tri-diagonal, and you're calculating the spline as it goes through all the knots. Well, you can actually do that with a finite difference here and use the Thomas algorithm. You can also do something that's called a strongly implicit procedure, and that means, oh, I can, instead of it being tri-diagonal, I can actually have a 5-diagonal. So there's a technique that I can use that allows me to actually wind up solving for this thing in one swoop, or a sweep, one calculational sweep through this thing, versus a Thomas algorithm where I would have to do 2 sweeps. Right? That's called the alternating direction implicit method. We'll get to that. You remember this, Taylor series. So here's a forward expansion and a backward. So here's the backward. I'm looking at I minus 1 as a position. And so here would be the Taylor series. If I'm looking at the I plus 1 position, that would be the forward. All right, so I can either from this extract out the first derivative or the second derivative. Actually, I can go higher if I wanted. But the class of equations that I'm dealing with in engineering, 99.9% of them are no higher than second order. Here's what I get from the Taylor series by truncating off the remaining terms. So that first derivative, this would be a backward difference. So it goes from point I to I minus 1. That would be a forward difference. I plus 1 to I. So that's a one-sided difference. Anybody remember what the order of accuracy is when I do one-sided differencing? It's first order. Right? Why would I want to do something like this? When I'm against a boundary, if I have a central difference, it requires an I plus 1 and an I minus 1. I don't have an I minus 1. So I could do a first order approximation along the boundary. And then when I'm internal, then I can go to the second one. First order, one-sided and backward approximation. That's why are they first order? We know that because, as we've said before, in the truncation, you find out that it's delta x or delta y, whatever it is. How do you get second order accuracy for the first derivative terms? You know that. Right? You're going to create a central difference, so you can subtract the first equation from the second. All right, so what happens is that you now have that approximation, and that goes from delta x now to delta x squared. So you're now second order accurate. So you see what that means? It requires a node at I plus 1 and a node at I minus 1, where in the one-sided difference, it only requires 2 nodes. Now, I can also improve the accuracy on these one-sided differences if I wanted to go here. You notice that they're second order, right? Either a forward or a backward. So here's a backward, here's a forward. So if I wanted to calculate the value there, I would need the value at I minus 1 and I minus 2. See? Or I plus 1, I plus 2. So where do we get these? from just expanding out the Taylor series. All right? The problem is that now I've got 3 nodes involved in here, and I want to keep the number of nodes down to a minimum if I can. Here's the second derivative term. All right, there's the central difference, and that's the second order accurate. So now I'm using I plus 1i and I minus 1 nodes. If I wanted to bump this up to 4th order, that's what it would look like. Now, how many nodes would I have involved? So instead of being a tri-diagonal, as you see right here, now I've got what? A 5. I can't use the Thomas algorithm anymore. Right, so I have to go to a different type of solver if I'm doing this implicitly, that is solving it as a matrix. I can also obtain an approximation for the 4th derivative term. It's very rarely used. The only time you would run across something like this is if you're solving something called the biharmonic equation. And I won't get into that, but if you get into fluids, just look up biharmonic, and you'll see that it's a 4th order equation that consists of one unknown. And you go, oh, that's kind of neat. So finally, I've reduced those number of unknowns in the equations in the Navier-Stokes set to one equation, one unknown. How the devil am I going to solve a 4th order equation? Because 2nd orders I can deal with. Well, that's what it looks like. So how many nodes do we have here? 1, 2, 3, 4, 5. So I'm now dealing with a 5 stripe that I have to deal with. That is a 5 diagonal matrix I'd have to solve. Okay. You notice that I had a time derivative term setting in there in those governing equations, right? Oops. Let's go back. The way you do time derivative terms, 99% of the time, is a forward in time. Now that's a one-sided difference. And the accuracy of this is 1st order, so that means it's accurate to delta t, not delta t squared. There's a way to do that. You can do a central difference, but you don't want to do that because of storage problems. So you want to do everything here in the derivative time as a forward approximation. The n plus 1 means it's unknown. The n means that it's known, or you've just calculated it before. Yes?
That's generally done, but could you do a 2nd order difference?
Sure. Yeah, you can do a central, and now, let's say you do a central difference on time. So I'd have a u I plus 1 minus a u, or u and n plus 1 minus a u and n minus 1. How many levels of that value of u do I need to retain? I need the u I plus 1, save those values. I need the u at n, I need to save those values. And I need to save the values from n minus 1. So if I have 1,000,000 nodes, that's 3 times, right? 3 times 1,000,000. I don't want to do that. I'll saturate the storage. If I have unequal grid spaces, but they're still orthogonal. Remember I was talking about this thing? If they're the same, it's uniform, but if they're not, then you have to say, okay, well this mesh is a little different from this one. How do I do that? Here's the expression for the 1st derivative and the 2nd derivative. Where did those come from? You did it before. Lagrange interpolation. Now, what happens if my spacing is uniform, is the same? Well, that's a delta x. Delta x is xi plus 1 minus xi. So that's delta x. That's delta x. It's the same. So that becomes, this thing collapses to a central difference that you saw before for a uniform mesh. So if you program or set things up to solve the gradients this way, you automatically cover the instances where you have equal grid spacing. But you've now covered it for unequal grid spacing. All right, these two expressions produce a 2nd order. This is what happens as I said, when it collapses down. So they look exactly like we saw. You should be comfortable in obtaining these expressions. Be sure you can derive these. All right? You did it once before. Be sure that you remember in the Taylor series. Forward, backward, subtract. What is the value for the first derivative or the second derivative for a central difference? All right, there are times when you want to use unequal grid spacing. That's what we did right there. Okay. That's what I mean by the molecule. So if you can remember this, then you've got me. All right, here's the node point in 2D. Here's the node point that's unknown. If I do a one-sided difference forward, I would use that point and that point. If I had a backward, I would use that one, either in the X or Y direction. If I do a central difference approximation, I would have that point and that point in the X direction, that point and that point in the Y direction. If I have a second derivative, I would have either those 3 points or those 3 points. That's what we refer to as the molecule. That's a good, easy way to remember this in establishing a finite difference approximation. That's an elliptic equation, all right? Here is second derivative terms. This is a Q, so would this be a Laplace or Poisson equation? Yeah, Laplace. Laplace, right? Wait a minute, how can that be? What's that?
It's constant.
So what?
It doesn't depend on X and Y, so.
Goes
It's
over
not-
here. I can put it on the right-hand side. That's a Poisson equation. I can make Q a function of X and Y if I wanted to. When del squared phi, or whatever the relation would be, equals 0, Laplace, when you have something setting here other than those second derivatives, Poisson equation. I want to discretize this equation using second order approximation. Here is the approximation for this term. Here's the approximation for this term. Here is the source, Qij. Now, what's all this stuff? What's all that? That's the truncation error. That's what you get right here from truncating the Taylor series for the second derivative. That's what you get for the y. Be sure you can derive this equation. Put a little check mark on that. All right. Any questions? What we've gone over? Finite difference method. You must know that one. That's one of the real constraints that you have here coming out of this course. You will not be at a loss at solving partial differential equations by doing a finite difference method. The last homework problem, I can tell you, will be solving for probably a heat diffusion type problem, and I will have you solve the two-dimensional PDEs for heat transfer. So you will have to use that discretization that I showed you, and then you'll have to do it either implicitly or explicitly. What do I mean? What's implicit mean? Everything is unknown, so you have to solve it using a matrix solver. The most efficient way, Thomas algorithm. You could do it as a Gauss elimination, but it'd take you forever. What do I mean by explicit? Only one unknown. Everything else is known. Sets on the right-hand side. So if I had that phi I minus 1 plus phi I minus 1, whatever, all those terms setting in there, well, we know where they set in space, but if I'm marching this in time, I didn't have the n, the superscripts in there. Did you notice? So if I set everything at n plus 1, that means, oh, they're all unknown. How am I going to solve that? That's what I mean by implicit. If I have only the unknown in ij and everything else is known, I move all that to the right-hand side, that's explicit. Why would I want to do an implicit versus explicit?
Implicit shows you go forever.
Converges faster. As you will start running things explicitly, there'll be constraints where you say, oh, I exceeded some limitation and this thing blows up. I can't do that. So it's easier to program and do parallel processing. But on the scalar machines that you're doing on PCs, you want to do things implicitly if you can. It's much faster. All right, that's it.